The condition originated in the pre-dawn hours of Tuesday, April 23rd, within the monitoring infrastructure of Miami's Eastern Drainage District, a network of 42 pump stations, 17 primary outfall structures, and approximately 230 miles of subsurface conduit serving the neighborhoods between Biscayne Bay and the interior canal systems. At 3:14 a.m., a scheduled calibration routine executed across the pressure transducers installed at major outfall points where drainage pipes discharge into tidal waters. These sensors measure the difference between internal pipe pressure and external water elevation to determine when gravity drainage is possible and when pumping is required to overcome tidal back pressure. The calibration routine, implemented as part of a system-wide upgrade completed 8 months earlier, adjusted the zero-point reference for each sensor based on a rolling 30-day average of tidal elevations recorded by NOAA monitoring stations in the bay. On this particular morning, the reference calculation incorporated an anomalous data set from the preceding 3 weeks, during which several tidal sensors had reported readings elevated by approximately 0.3 feet due to a separate instrumentation issue that had not yet been identified or corrected. The calibration routine interpreted these elevated readings as a genuine shift in baseline sea level and adjusted all drainage system sensors upward by a corresponding margin. When the routine completed at 3:41 a.m., every outfall pressure transducer in the Eastern District was reporting external water elevations approximately 4 inches higher than actual tidal conditions, a discrepancy that fell within the tolerance bands programmed into the system's alert thresholds and generated no supervisory notifications. The immediate consequence of the calibration error was a systematic bias in the control logic governing the 218 backflow prevention valves installed at pipe terminations throughout the district. These valves, commonly referred to as flap gates or tidal check valves, are designed to allow drainage water to flow outward when internal pressure exceeds external pressure, but to seal closed when external tidal pressure rises above the internal drainage level, preventing saltwater intrusion into the freshwater conduit network. The valves operate passively under most conditions, opening and closing in response to differential pressure without active control. But 47 of the larger installations include motorized actuators and position sensors integrated with the central monitoring system to provide positive closure during predicted high tide events or storm surge conditions. The control algorithm for these motorized valves evaluates the pressure differential reported by the outfall sensors and commands closure when external pressure is projected to exceed internal pressure within the following 30-minute window, based on tidal prediction tables and real-time sensor data. With the sensors now reporting artificially elevated external pressures, the algorithm began issuing premature closure commands to motorized valves across the Eastern District, starting at 4:52 a.m., during a tidal phase when actual bay elevations were still 14 inches below the levels at which closure would normally be warranted. The valves responded to these commands within their specified actuation time of 90 to 120 seconds, transitioning from the open position to fully closed and latching in place. The passive flap gates at non-motorized outfalls remained responsive to actual pressure conditions and stayed open, but these smaller diameter discharge points represented only 38% of the district's total outflow capacity. Between 5:30 a.m. and 7 a.m., during the period of lowest tidal elevation, when gravity drainage is typically most effective, the Eastern District's ability to discharge accumulated runoff was reduced to approximately 40% of normal capacity due to the closure of the motorized valve network. This reduction went undetected because flow rates through the open passive valves remained within historical ranges for low runoff conditions, and the overnight period had been dry with no precipitation to generate significant inflow to the system. The first rainfall began at 7:23 a.m. as a weak convective development moving inland from the Atlantic, producing light to moderate precipitation across a 12-square-mile area of the Eastern District at rates ranging from 0.4 to 0.7 inches per hour. Under normal drainage conditions, this intensity of rainfall would be managed entirely through gravity flow to the bay, with runoff entering catch basins, flowing through the subsurface pipe network, and discharging through open outfall structures without requiring pump activation. The drainage design standards for this district specify capacity to handle a 2-year recurrence interval storm, defined as 2.8 inches of rainfall in a 3-hour period, through gravity drainage alone before pump stations are needed to maintain acceptable street flooding limits. The morning rainfall was well below this threshold, representing approximately 15% of the design storm intensity, and municipal weather monitoring systems classified the event as routine precipitation, requiring no special operational response. However, with 62% of outfall capacity unavailable due to the closed motorized valves, the actual drainage capacity of the system had been reduced below the inflow rate generated by even this modest rainfall. The accumulation of water within the subsurface drainage network proceeded in a characteristic pattern determined by the topography of the pipe system and the distribution of inflow points. Water entering through catch basins flowed downgrade through collector pipes toward the larger trunk lines that convey runoff to outfall locations. Under normal conditions, this flow maintains velocity sufficient to prevent sediment deposition and provides continuous discharge at the outfalls, creating a steady-state condition where inflow and outflow rates remain balanced. As the trunk lines approached the closed motorized valves, flow velocity decreased and water began to accumulate in the pipes, gradually filling the available storage volume and creating a rising hydraulic grade line that propagated backward through the system. By 8:15 a.m., pressure sensors in several trunk lines were recording static head elevations 6 to 9 inches above the levels typical for comparable rainfall events, indicating that water was being retained in the pipes rather than discharged. The pump stations distributed throughout the district are designed to activate when water levels in their associated wet wells rise above predetermined set points, typically triggered when gravity drainage becomes insufficient due to high tides, heavy rainfall, or both. However, the control logic for pump activation includes an interlock condition that prevents pump operation when the discharge point pressure exceeds safe pumping head limits, a safety feature intended to prevent pumps from operating against closed valves or excessive back pressure that could damage equipment or cause pipe ruptures. The same artificially elevated pressure readings that had triggered valve closure now indicated to the pump station controllers that discharge conditions were unfavorable for pumping, and the interlock conditions remained active even as water levels in the wet wells began to rise above normal operating ranges. Street-level flooding was first documented at 8:47 a.m. at the intersection of Biscayne Boulevard and Northeast 17th Street, where a traffic camera recorded water depths of approximately 4 inches extending across the eastbound lanes and into the adjacent parking areas. The water accumulation at this location was attributed by initial observers to a blocked catch basin, a common occurrence during rainfall events when debris accumulates over drain grates, and a street maintenance crew was dispatched to clear the obstruction. The crew arrived at 9:08 a.m. and found the catch basin grate clear of debris with visible flow entering the drainage system, but water continued to accumulate in the street despite the apparently functional inlet. Additional reports of standing water began to appear in the municipal service request system between 9:15 a.m. and 9:45 a.m., documenting similar conditions at 11 locations across the Eastern District, all characterized by depths of 3 to 6 inches, slow or absent lateral flow, and no obvious blockages at drainage inlets. The distribution of these locations corresponded closely to areas served by the larger trunk lines that connected to motorized valve outfalls, while areas served by passive valve outfalls showed minimal water accumulation despite receiving comparable rainfall. By 10 a.m., the rainfall had decreased to intermittent light showers with rates below 0.2 inches per hour, and total accumulated precipitation across the affected area ranged from 0.6 to 1.1 inches, well within the system's design capacity and comparable to dozens of similar events that had occurred without notable flooding in previous years. The Miami-Dade Water and Sewer Department's Drainage Operations Center became aware of the anomalous flooding pattern at 10:17 a.m. when a duty supervisor reviewing the morning service requests noted the geographic clustering of reports and the unusual description of standing water at locations with confirmed functional catch basins. The supervisor accessed the SCADA system interface that provides real-time monitoring of pump station status, valve positions, and sensor readings across the drainage network. The display showed that 16 of the 23 pump stations in the Eastern District had wet well levels above the primary activation set point but were not running, with status indicators showing interlock active, discharge pressure high as the reason for non-operation. This condition was consistent with high tide or storm surge events when pumping against elevated bay levels is temporarily suspended, but tidal data from NOAA stations indicated current bay elevations were at mean lower low water, approximately 1.8 feet below mean high water and well within normal pumping range. The supervisor initiated a manual status check of the motorized valve network and found that 41 of the 47 valves were in the closed position, with commanded closure times ranging from 4:52 a.m. to 5:37 a.m. The valve position data was cross-referenced with tidal predictions, revealing that the closure commands had been issued during a period when bay elevations were between 0.9 and 1.3 feet below the levels that would normally trigger precautionary closure, suggesting a systematic error in the pressure sensing or control logic rather than isolated equipment failures. A conference call was convened at 10:52 a.m., including the drainage operations supervisor, 2 control systems engineers, and a representative from the SCADA system vendor to diagnose the apparent sensor or logic malfunction. The engineers remotely accessed detailed telemetry logs from 6 representative outfall pressure sensors and compared the reported external water elevations to actual tidal measurements from nearby NOAA stations. The comparison revealed a consistent offset of 0.28 to 0.34 feet between the drainage system sensors and the reference tidal gauges, with the drainage sensors reporting higher values in all cases. This offset was traced to the early morning calibration routine, and a review of the calibration algorithm's data sources identified the corrupted tidal reference data that had caused the systematic bias. The immediate remediation required manual override of the valve closure commands and resetting of the calibration offsets to restore accurate pressure measurements, but implementation of these corrections required sequential access to each valve controller through the SCADA network, a process complicated by the distributed architecture of the system and the need to verify safe operating conditions before reopening valves that had been closed for more than 5 hours. The decision was made to begin valve reopening with the largest capacity outfalls serving the areas with the most severe street flooding, prioritizing restoration of drainage function over systematic correction across the entire network. The first valve reopening command was issued at 11:24 a.m. to a 72-inch diameter outfall at the terminus of a major trunk line serving the Biscayne Boulevard corridor. The reopening of the motorized valves produced measurable but gradual relief of the accumulated water, as the drainage system required time to evacuate the volume stored in subsurface pipes and to overcome the static head that had built up during the closure period. Flow monitoring at the first reopened outfall showed initial discharge rates of approximately 1,800 gallons per minute, well below the pipe's capacity of 6,000 gallons per minute, indicating that the hydraulic grade line in the upstream network had not yet developed sufficient slope to drive higher flows. Street-level water depths began to decrease within 15 to 20 minutes of valve reopening at locations directly served by the affected trunk lines, but the rate of decline was limited by the relatively small gradient between the standing water elevation and the drainage inlet elevations, which in many areas differed by only 2 to 4 inches. The passive physics of surface water movement meant that final clearance of standing water from street surfaces depended on achieving complete drainage of the subsurface system, as water would continue to seep into catch basins only as long as the pipe network maintained capacity to receive it. By 12:30 p.m., 28 of the 41 closed motorized valves had been manually reopened, and pump stations were being sequentially released from interlock status to assist in evacuating the accumulated volume from wet wells and upstream pipes. Street flooding reports peaked at 37 documented locations between 11:45 a.m. and 12:15 p.m., then began to decline as drainage function was progressively restored across the Eastern District. The residual effects of the drainage interruption persisted through the early afternoon as subsurface pipe storage volumes were gradually evacuated and street surfaces dried through a combination of drainage inlet capture and evaporation. Water depth measurements taken by field crews between 1 p.m. and 2 p.m. showed maximum remaining accumulations of 1 to 3 inches at 17 locations, primarily in localized depressions where street grading directed surface flow toward catch basins that were still working to drain the upstream pipe network. Traffic disruptions associated with the standing water were documented through automated traffic speed monitoring, which recorded average vehicle speeds reduced by 12 to 18% on affected street segments during the peak flooding period, with speeds returning to within 5% of normal by 2:30 p.m. No water intrusion into buildings was reported, and maximum recorded water depths at any location did not exceed 7 inches, well below the typical threshold of 12 inches at which vehicular access becomes significantly impaired for standard passenger vehicles. The rainfall concluded entirely by 1:45 p.m., with total event accumulation ranging from 0.7 to 1.2 inches across the Eastern District, representing a routine precipitation event that occurs approximately 40 to 50 times per year in the South Florida climate. The final motorized valve was returned to normal automatic operation at 3:18 p.m., and all pump stations were restored to standard control mode by 4:05 p.m., marking the completion of manual intervention to restore system function. Post-event analysis conducted over the subsequent 2 weeks included detailed review of SCADA system logs, calibration routine source code, tidal reference data quality, and valve actuation sequences. The documentation identified the corrupted NOAA tidal dataset as originating from a sensor malfunction at the Virginia Key monitoring station that had persisted undetected for 19 days prior to the event, during which time the sensor reported consistent positive bias, averaging 0.31 feet above actual water levels. The drainage system's calibration routine had incorporated this biased data without validation against alternate tidal references or outlier detection algorithms, propagating the error throughout the pressure sensor network. The total duration of impaired drainage capacity was calculated as 6 hours and 34 minutes from the first premature valve closure to the final valve restoration, during which time the Eastern District's discharge capacity operated at 38 to 42% of normal for gravity drainage and 0% for pump-assisted drainage. The affected area comprised approximately 14.2 square miles, with an estimated population of 63,000 residents and daytime commercial activity involving approximately 22,000 employees and visitors. Engineering review of the system's performance noted that street flooding had occurred at precipitation intensities between 0.4 and 0.7 inches per hour, substantially below the 2-year design storm threshold of 0.93 inches per hour averaged over 3 hours, indicating that the drainage capacity margin intended to accommodate routine rainfall had been entirely consumed by the valve closure condition. Recommended modifications included implementation of tidal data validation checks prior to calibration execution, reduction of pressure sensor alert thresholds to detect anomalous readings before they affect operational decisions, and addition of manual confirmation requirements for valve closure commands issued outside of predicted high tide windows or active weather warnings.